Hello, this is MEI Further Maths Core Pure. We're in the second vectors section and on the second video on the equation of a plane in Cartesian form. You can watch the video straight through, but you will probably find it helpful sometimes to pause the video and try things out for yourself before continuing to watch. We're going to look at finding the Cartesian equation of a plane from a position vector of a point in the plane and the normal vector of the plane. This is a really neat result. OK, we've got our general point R, x, y, z, and a normal vector n, which is n1, n2, n3. We're going to use this equation, which we found in a previous video, r dot n is equal to a dot n. So, let's write that out. R is x, y, z, dot n1, n2, n3, and that's equal to a dot n. Now, a dot n is just a number, so we won't worry about that. Let's have a look at the left-hand side. That's x n1 plus y n2 plus z n3, and that has to equal this number a dot n. So if I rewrite this in the usual way with the x, y and z second, we've got n1x plus n2y plus n3z is equal to a number. I'm going to call that number minus d so that I can then get the usual form of the general equation, which is this, where d is equal to minus a dot n. So you can see that the coefficients of x, y and z in the Cartesian equation of the plane are the components of the normal vector. That means that we can write down the normal vector of a plane straight away from its Cartesian equation. It also means that we can work out the Cartesian equation of a plane very quickly. Here's an example. I've got a point A, 1, 2, 0 in my plane, and I've got the normal vector to the plane. So, the normal vector is 2, 5, 3. And the position vector of my point is 1, 2, 0. Using our equation r dot n is equal to a dot n, I get this. General point R is x, y, z, dot my normal vector 2, 5, 3 is equal to the position vector of my particular point 1, 2, 0, again dotted with the normal vector 2, 5, 3. So that gives me 2x plus 5y plus 3z is equal to 2 plus 10 plus 0, which is 12. And there is the Cartesian equation of my plane. I didn't really need to write down this left-hand working because I knew from the previous result that the coefficients of x, y and z were going to be 2, 5 and 3 respectively, straight from my normal vector. All I needed to work out was a dot n. So, a summary. The vector equation of a plane using the normal is r minus a dot n equals 0, or more usefully, r dot n is equal to a dot n. And the Cartesian equation of a plane is n1x plus n2y plus n3z plus d equals 0, where n1, n2, n3 is the normal vector of the plane, and d is equal to minus a dot n. Here's a problem for you to try. Pause the video while you have a go at it. OK, to compare the planes it helps to have them all in the same form. So we'll write down the Cartesian equation of each one. Plane A is x plus 2y minus z equals 4. Plane B is 2x plus 4y minus 2z equals 4. And you can see that we can divide through by 2 to get x plus 2y minus z equals 2. And therefore planes A and B are parallel to each other. Plane C is different. We get minus x plus y plus z equals minus 2. For plane D, we get minus x plus y plus z equals 2. So that's parallel to plane C. Plane E is minus x plus 2y plus z equals 4, which is quite different from all of the others. And then plane F, x minus y minus z equals 2. Multiplying through by minus 1 gives us minus x plus y plus z equals minus 2. And you can see that C and F are in fact the same plane. So C and F are the same plane. A and B are parallel. And D is parallel to C and F, which are the same as each other. And there's a bonus question. See if you can work out which ones are perpendicular. If you get stuck on this, you'll find that in the next video there will be a hint. There are more notes on integral or in your textbook on the equation of a plane in Cartesian form. That's the end of this short video. The next video in the series is on the angle between two planes.